So you want to get heat from one place to another. So you have something that's hot and something that's cold. Okay, so that's going to be T1, T2. We're assuming T1's greater than T2. And so we want to get heat from one to the other. There's several different ways of doing that. One is you just take an object, put in contact with H1. These molecules are vibrating. If they're vibrating more than that, they hit it, work is done, and energy, heat flows into there. Now it's going to it's going to keep going until the flow of heat in equals the flow of heat out. That's equilibrium, at which point it's going to be the same temperature as the other object. Now you move it over here, and if it's hotter than that, then more heat's going to flow this way than that way. It's going to keep going until it's equal. Now it's the same temperature, but it had to lose heat. So heat went from one to the hot to the cold. That is convection. In this case, it's forced convection because we're moving one thing to the other. You could have natural convection in that you heat something, it expands. For example, if something expands, it's going to rise. You have buoyancy. Hot air will rise, and then cool air is going to sink because it's greater density, and you have natural convection like that. Another way that you can get heat transferring from one place to the other is the molecules vibrate and it radiates heat out. Now, we'll talk more about that in physics too, about how radiation works. Third way that heat transfers from one place to the other is simply you have a conduit between the two. And so you have the hot thing and the cold thing. The molecules here are vibrating more than the molecules on the other side. And so what happens is these molecules are vibrating more, and the energy is transferred molecule to molecule. And so heat goes from one to the other. That is conduction. So the question, how much heat goes from one to the other? Well, it actually depends on several things. If I had two conduits between the two, then more heat would flow. And so in that sense, you can think of it as proportionate to the area. The more area, cross-sectional area the heat's going through. Also, the greater the temperature difference between hot and cold. Okay, so the difference between hot and cold there, that makes a difference. The greater the difference, then the faster the heat's going to go, the more heat's going to go. It's going to relate how long it's in contact. So we have T. Okay. It also depends on L inversely. And the reason it's inverse is that the farther apart they are, the more molecules there are in between that have to share. And each one is basically, you can imagine that halfway between is going to be half the temperature, and then that's a quarter of the temperature, a quarter of the way between, and so forth. Well, the bigger L is, the farther apart different temperature molecules are, and we know that the difference in temperature is part of what drives this. And then finally, it's proportionate to a quantity that is a property of the material. So this is a coefficient of thermal conduction right here. And so what we do is, this gives us this. Now, the interesting thing is that these are all properties here of how long and so forth. We can divide through by T, so Q over T is going to be power transfer, and so that will be Ka delta T over L. That's actually how it's written in your book. Now, notice the power, or even the heat, is inversely proportionate to L over K. So we actually define L over K to be the thermal resistance, and the symbol we use for that is R. So we call that the R factor. And so when you're putting insulation in your house, then the R factor is going to be related to how thick the insulation is and the type of material you have for the insulation. So in other words, if you have a material that's twice as conductive, in other words, K is half, then L has to be twice as thick, okay, in order to get the same R factor. The bigger the R factor, the less heat, because what you see is that the heat that transfers, or we can even do the power transfer, is going to be equal to A delta T over R. Okay. And so that the bigger the R factor, the less the power. So when you're insulating your house, the bigger the R factor, then the better the insulation, the less your AC or heater has to run to cool or heat the house, depending on what time of year it is. We can do examples of this. For example, you can imagine that you had a cooler right here, and the cooler was made of styrofoam, and you know the thickness of it, and you put some ice in here, and you know the temperature of the ice melts, you know the temperature outside, and so you can actually find out, solve for T, you know, the heat, that's going to be MC delta T plus MLF. So assuming that the ice is already at 0 degrees Celsius, then that's going to be that, and so that's going to be equal to Ka delta T times time divided by L. L is going to be the thickness of your styrofoam. K is going to be the thermal conductivity of your styrofoam, which is actually pretty low. Delta T, the difference in temperature between inside and outside. And so A is going to be the total surface area, top, bottom, and sides. And that would give you, here, you could solve for T, the how long it would take for the ice to melt. Now, one thing you notice is that if you have a certain amount of ice, that the smaller A is, the less heat goes through. And so the longer it's going to take for the ice to melt, because the time it takes the ice to melt is LQ over Ka delta T. So if you were doing this, the thicker the cooler, the thicker the walls, the cooler, the longer it takes for the ice to melt. The less conductive the cooler, because different coolers are made of different materials, the less conductive, then the longer it takes to melt, and the smaller the cooler. The bigger the surface area of the cooler, then the more area there is for heat to go through. So the idea is, if you're trying to keep, a drink cold in a cooler or something, then you want a cooler that's just barely the size that you need it to be. You don't want to have a huge cooler, unless you fill the huge cooler with something, fill it with ice or something else that can take the heat. But the cooler that's too big is going to be less efficient than one that's just right size. And of course, the bigger the difference between inside and outside, then the less time it takes to cool. So a hot day, it melts quicker than a cool day. Okay, I'm not going to do that example numerically, but you can sort of see how that would work.